what we're going to do is we're going to look at our solubility equilibrium. Now, solubility equilibrium is a special type of equilibrium that forms between slightly soluble salts and the ions in solution. Last year in grade 11, when we were talking about ionic compounds, we described them as soluble or insoluble. Turns out that most of the salts that we called insoluble do dissolve in water, but usually at very low amounts. And so, as a result, if we have their ions in solution at any significant level, we might get the formation of a precipitate. What happens with these solutions is that over time, they'll establish a dynamic equilibrium where the concentration of my ions in solution and the mass of my solid at the bottom remain the same. And I can recognize this by things such as the color of the solution. Now, a solubility equilibrium can be established from either direction. So we could, for example, start off with adding some salt to water. So I could add some sodium chloride to a certain amount of water, and I could let it come to equilibrium. And when I first add the solid to water, the rate of dissolving will be greater than the rate of crystallization. This is because we have no ions in solution initially to precipitate out. But as the solid dissolves, we'll get more ions into solution, and so my rate of dissolving will decrease as I approach my saturation point, and my rate of crystallization will increase. Once equilibrium is reached, my rate of dissolving is equal to my rate of crystallization. And at this point, the concentration of the ions in solution will be constant, and the mass of the solid at the bottom will also be constant. Now, the second way that I could establish this equilibrium is I could combine two solutions, each which contain one of the ions that results in the formation of my slightly soluble salt. So, for example, if I combined a solution of sodium chloride with a solution of silver nitrate, initially I'll start off with just silver ions and chloride ions. And in this setup, my rate of crystallization will be greater than my rate of dissolving because I don't have any ions. I only have ions to crystallize, and I have no solid to dissolve. But once equilibrium is reached, once again, my concentration of ions will remain the same, my mass of my solid at the bottom will remain the same, and my rate of dissolving will equal my rate of crystallization. Now, last year we talked about solubility, and we talked about it as being the maximum amount that will dissolve at any given temperature. Well, if we know this maximum amount that will dissolve at any temperature, it'll allow us to determine the concentration of the ions. So for example, if I know I have my silver chloride equilibrium, my solubility, in this case, of my silver ion and my concentration of my chloride ion, both in equilibrium, will be equal to the solubility of the silver chloride. Now, this is just really a shortcut, and what it does is it allows us to simplify the relationship between the ions because we know that they are determined through our mole ratio, given that they're in the same volume. So, for example, my concentration of my nickel ions at equilibrium will be equal to the concentration of the nickel 3 sulfate that dissolves in water times the volume, gives me my moles of nickel 3 sulfite times the mole ratio divided by the volume. Now, since the volume is the same, it allows me to simplify to concentration times mole ratio. I apply my mole ratio. Now, if I just get rid of my units, I get that my concentration of my nickel 3 ion is equal to 2 times the concentration of my nickel 3 sulfite. And I can rewrite this so that it's similar to what our solubility statement, where we compare the amount of ions to the concentration of the slightly soluble salt. Now, we can use this because it will allow us to determine the concentrations. So, for example, if I have a copper phosphate and I'm told the solubility, and remember solubilities from the solubility curve are usually expressed in grams per 100 milliliters, we could turn it into a concentration. And then we could use our understanding of solubility equilibrium to determine the concentration of each of the ions. So first thing I do is write out my balance equation showing the dissociation of the slightly soluble salt. And I have an equilibrium symbol to show that I understand that it's a dynamic equilibrium. Then I'm going to write my solubility statement. And again, my concentration of my calcium phosphate is 1/3 of the calcium ions, because for every one of these it dissociates, I'm going to get 3 calcium. So if X dissociates, my concentration of my calcium would be 3X. So 1/3 times 3X would be X, which is X. And similarly, for every one of these, I would get 2 phosphate. So if X moles dissociate, I'd have 2X. So I multiply by 1/2, so again, it's the same. So this is just an application of using my mole ratios simplified. So the first thing I'm going to do is I'm going to take the concentration as expressed per grams per 100 mils and turn it into a concentration in terms of moles per liter. And to do that, I just divide by the molar mass and then convert my volume to liters. So now I have my concentration of my calcium phosphate. And then I can use my solubility statement to get the concentration of my calcium ions and the concentration of the phosphate ions. Now that we understand how to use our solubility statements, what we can do is we can look at how we can predict our concentrations if we don't know our solubility. And for this, we'll use what we call a solubility product constant, or KSP. This is similar to our equilibrium constant we did before, but slightly different. And the difference is that regardless of the direction at which equilibrium is established, we always start off with my solid as a reactant, and my ions are as product. Because what this does is when I write my equilibrium expression with a concentration of the products over the concentration of reactants, since my solid is in the reactants always, it would be over 1. Okay. So this is, we know our KSP value. Now, we can, just like before, if we know the equilibrium concentration of our ions, we can get our equilibrium constant, or our solubility product constant, KSP in this case. So here we're told how much silver chloride is in 1 liter of a saturated solution, and we're asked to determine our KSP, our solubility product constant. So the first thing, like always, is we need a balanced equation. We'll write our equilibrium expression like we do. And now here's the one difference that we have from before. We're going to always write a solubility statement so that we know the relationship between the solubility of my salt and the concentration of the ions. Now that I know this, I can use what I know about the concentration of my salt, or the amount that's dissolved, to determine its concentration. Now that I know the salt concentration through my solubility statement, that tells me my concentration of my 2 ions. So now that I know their equilibrium concentrations, I can substitute that into my equilibrium expression and get my KSP value. If we know the KSP value, we can go the other way and determine the solubility or concentration of the ions at equilibrium. So just like before, first step, we write our balanced chemical equation, our equilibrium expression, our solubility statement. And now in this case, because we don't know the solubility and we're trying to determine it, what we'll need to do is we'll need an ice table. And prior to any of the salt dissociating, I have none of either of the 2 ions. Once some of it dissociates, for every one of these that dissociates, I'm going to get 1 magnesium and 2 hydroxide. So that I have my equilibrium concentrations. I can then take those and substitute them into my equilibrium expression. So X would be substituted in for the concentration of magnesium ions, 2X for the concentration of hydroxide ions. We do our math, we get our X value. So now I know my concentration of my magnesium ions at equilibrium, and I know the concentration of the hydroxide ions, And if I use this in relation to my solubility statement, I can get the solubility of the magnesium hydroxide.